I'm Anil Kumar. Welcome to my series on annuities. We'll discuss what are annuities and how to calculate their future value in this particular video. As you know, annuity is a sequence of equal payments made at equal interval of time. As shown in this particular diagram here, these are the intervals numbered as 1, 2, 3, 4, and 5, and equal payments of 1200s, for example, are being made at these points. We'll look into how much interest do they accumulate and what is the future value of all these regular payments being made. As you can see, that the interest accumulated forms a geometric sequence, and therefore there is a very close relation between the future value of an annuity with the geometric sequence. We are going to explore the geometric sequence, find the sum of elements, and connect it with the future value of annuity. We'll actually work most of the time with ordinary annuities, where the payments also coincide with the compounding periods. Future value is definitely the value which you are interested in when you're accumulating interest over a period of time on fixed regular payments. How to rearrange this formula and find the regular payments is another part which we'll look into. Sinking funds are also annuities which have a purpose. And the major purpose here is to deposit something in a fund, and the whole amount can be later used as a lump sum for making payments. Annuity due. So we'll end this particular video with a variation to ordinary annuity. In ordinary annuity, the payments are being made at the end of the interval, and the compounding always is done at the end of the interval. In annuity due, we'll see what happens when the regular payment is made in the beginning of the interval. So that's a very interesting twist to this concept. So let's begin with the formulas which we'll be exploring. As you know, geometric sequence means a sequence which is kind of a times r, ar square, ar cube, and so on, where a is the first term and the common ratio is r. The nth term is ar to the power of n minus 1. Now, geometric series sum is given by the formula S of n equals to a times r to the power of n minus 1 divided by r minus 1, and for sure r cannot be 1. Future value of an ordinary annuity, where n is the total number of periods in the terms and interest rate of I per compounding period, right? So when we say compounding period, it is the interval within a year. So we'll divide by n are the number of intervals within a year. The future value, the formula which we are going to derive here, is equals to r times 1 plus I to the power of n minus 1 divided by I, where I is the decimal equivalent of the rate of interest per term. Geometric series sum and the annuity, they are very much related, as you can see with the two formulas we're talking about, where A is equal to R, the capital R, the regular payments, and R is 1 plus I, the ratio in which it gets multiplied. Also remember the compounded amount, the compound interest formula. So the amount when compound interest is in place is principal into 1 plus I to the power of n. We'll have examples where the combination of annuity with compound interest will be considered. As I was saying, annuity is due, and to find their future value. Since the investment is being done right in the beginning, we have one extra compounding period, and so the exponent is changed to n plus 1. However, we are not making an extra payment, so minus r. That is how you can relate with the formula of ordinary annuity. Let's begin with some examples now. Example 1. It is based on geometric sequence. Find the sum of the series 1000 plus 1000 times 1.04 plus 1000 times 1.04 square plus 1000 times 1.04 cube and so on till, so we have considered 6 terms till 1000 times 1 plus 0 4 to the power of 5. Correct? We need to find this sum. So in this particular case, this is a geometric sequence where there are 6 terms. The first term A is 1000 and the common ratio R is 1.04. Therefore, the sum of the 6 terms will be S of n equals to A r to the power of n minus 1 divided by r minus 1. And so you get the sum as 6632.98, right? Now, let's talk about the annuities, some definitions. Annuity, as we had been saying, is the sequence of equal payments made at regular intervals. Simple annuity is an annuity in which payments coincide with the compounding periods. And ordinary annuity is a simple annuity in which the payments are made at the end of each interval. Payment periods or the payment interval is the time between the payments, and they have to be consecutive, right? The term of an annuity is the time period from beginning of the first payment interval to the end of the last payment period. Future value of the annuity is the compounded amount at the end of the term. So let's have an example to find the value of an ordinary annuity. Example 2. Ordinary annuity and geometric series connection. $1,200 is deposited at the end of each year for the next 5 years in an account paying 6% per year compounded annually. Find the future value of the annuity. So in this, let's try to understand the basic concept. This is an example of ordinary annuity. As equal payments of $1,200 are being made at the end of each period, and the frequency of compounding matches with the frequency of the payments. The term of the annuity is 5 years, beginning from 1st January of the year when the first payment is deposited to 31st December of the year. Okay? Now, let's continue with this example and see how it really affects the whole scene. So we are talking about $1,200 is deposited at the end of each year for the next 5 years in an account paying 6% per year compounded annually. We need to find the future value of the annuity. So now, the first payment will be compounded 4 times. You see the timeline here? This is called the timeline. So when you start, we normally write that as the starting point as 0, right? So this is, we'll always mention this as 0. Now at the end of the very first year, the first installment, a regular payment of $1,200 is made. Second year again $1,200, then third, fourth, and fifth year, $1,200 payment is being made. So end of 5 years, $1,200 has been paid. No interest is earned on this because this has just been paid. However, at the end of 4 years, whatever was paid on that we earn 1 year interest, which is 1,200 into 1.06, 6% is the interest. Therefore, the amount, which will be the future value of $1,200 deposited last year, will be 1,200 times 1.06. And 2 years back, The money deposited earns interest compounded for two terms, right? So it'll be 1200 into 1.06 to the power of 2, which is squared. And that which was deposited the second year and will have exponent of 3, and which was deposited initially $1,200. It stays there for 1, 2, 3, and 4 terms, 4 periods, and therefore the amount will be equivalent to 1200 into 1.06 to the power of 4. So if we add all these amounts together, we get the future value of all these recurring deposits being made at the end of each year, right? So that is how you're going to calculate the future value as shown here. Future value is the sum of all these terms. And definitely this is a geometric sequence in which the first term is $1,200 and then we have a ratio of 1.06. So 1.06 to the power of 5, right? Minus 1 divided by 1.06 minus 1, and that gives you the solution or the future value of 6,767,6764.51. Perfect. So that is how you would actually get the future value. Now, this particular method of doing or finding the future value helps us to come out with a formula also, correct? So now we do have a formula for the future value of an annuity, which is related to this, which we are going to now write down. So example 3 is basically to derive the future value formula and to use it once again with another example. A father opened a saving account for his daughter in the day she was born. He plans to he plans to deposit, you can say $500 at the end of each 6-month period in an annuity that earns 5% per annum compounded semi-annually over the next 18 years. What will be the future value of this annuity? How much investment income did he earn? So again, this time we have deposited regularly fixed amount of 500 at the end of the period, and therefore it's again ordinary annuity. So we can say that the recurring deposit is of $500. Interest rate we have to calculate per period. Now, since this is 6 months, semi-annually, right? So twice in a year. The compounding rate being 5% per annum, compounded semi-annually. So therefore, we are going to divide this 0.05, the decimal equivalent, by 2 to get the interest rate during the period of compounding, which is 0.025 as we did in compound interest also, right? The number of compounding periods will be twice the number of years since the deposits were made 36 times and the amount will be compounded 36 times. The future value, as we derive the formula, will be r times 1 plus I, that is a multiplication factor to the power of n minus 1 divided by I, right? So that is the formula for the future value. Substituting the values, we can actually calculate that the future value for this particular investment is 28,650.71 cents, right? So that is how we are going to do part A. Now part B is how much investment income did he earn? That is to say, how much interest did he earn? So to find the interest, what we can do is we can just subtract what was actually paid in these 36 installments, recurring deposit of 500 each. So if you take up or subtract that from the future value of the investment, you know how much interest was earned, which comes out to $10,560.71. Perfect. So I hope now the concept is clear. This formula you can directly correlate with the geometric series formula, the sum of geometric sequence, and then it becomes simpler to work with. Let's take another example here. In example 4, we'll recalculate the value of regular deposits, this time knowing what other parameters are. The question here is Rishi wants to make monthly deposits into an account that guarantees 6% per annum compounded monthly. He would like to have 300,000 in the account at the end of 25 years. How much should he deposit at the end of each month? So now the regular payments will be monthly at the end of each month. Interest is 6% per annum, also compounded monthly. They are coinciding. It's an ordinary annuity, right? Rearrange the formula to find the value of the monthly deposit. We could do that. Now we know that the formula is basically future value is equals to r times 1 plus I to the power of n minus 1 over I. So we can actually rearrange this formula, substitute the values and calculate. So that is one option. What we really know is that the future value should be 300,000 interest rate monthly. So for the period, it will be 0.06 divided by 12, which comes to 0.005. Number of compounding periods, since it is for 25 years monthly, we'll multiply 25 by 12. N value is 300. Now you can also directly substitute the values and rearrange it later. So the future value of 300,000, we know the interest rate per period is 0.005, number of times it's compounded is 300, and substituting this value, we can now get 300,000 is equals to R times 692.99. So R is the ratio of 300,000 to 692.99, which is 432.91. So Rishi would have to deposit $432.91 at the end of each month in order to have 300,000 in the account in 25 years. So I hope that is absolutely clear. Now, you could actually rearrange the formula, then substitute and also directly calculate the values. Example 5. We'll combine this annuity concept with the compound interest in this particular example. Now, this example is very important from examination point of view. A 50-year-old person puts $1,000 in a retirement account at the end of each month until he reaches 60. If the account pays 8% per annum, interest compounded monthly, find the amount in the account when the person retires at the age of 65. So you will notice that this has combination of two things. From 50 to 60, it's kind of an annuity where a regular payment of $1,000 is being made at the end of each compounding period, right? So it's an ordinary annuity. Now, once that deposit has been made, it sits there and then earns that compounded interest for another 5 years. So at the age of 65, we have to find out the future value of this deposit, correct? You can actually pause the video at this stage, answer the question, and then look into my suggestions. So here is the solution. In this example, we have an annuity of 10 years followed by compounded growth for another 5 years at the interest rate of 8% per annum compounded monthly, correct? So initially, for those 10 years, we have R value as 1000, interest rate 8%. So 0.08 divided by 12, monthly period was 12. Number of compounding periods will be 12 times 10, which is 120. So the future value is, substitute the values in this particular formula, which we derived earlier from geometric sequence. So we get 1000 times 1 plus 1 over 150, right? So we use that fraction to the power of 120, which is n value, divided by 1 over 150. The future value comes out to be 182946.04. Right, so now that value is there when he was 60. This value sits there, that amount is there in the account, and it earns compound interest for 5 years and grows. So let's find what is the value of this investment after 5 years. So interest being paid again is the same, 8%, and therefore on the compounding period, 60, 5 years into 12, we can say that the amount will be principal into 1 plus I to the power of n. Substituting the values, we can calculate the answer, which comes to 272561.37. Okay? So that is how you're going to answer such questions. So $272,561.37. So I hope this concept is absolutely clear, right? Now, in question number 6, we are again discussing another concept which is very important from examination point of view. Normally, you may find many questions which are asking more than one thing in examination style test, right? Example 6. We'll also learn about the sinking funds, right? Peter bought a car. He agreed to pay a lump sum of 40,000 after 5 years. Until then, he pays 8% simple interest semi-annually, right? So for 5 years, he's paying only a simple interest 8% on 40,000. This amount of 40,000 equivalent will be, this amount of 5,000 will be actually paid after 5 years, correct? So that is the question. Now what you need to find is A, find the amount of each semi-annual payment. B, Peter sets up a sinking fund so that enough money will be present to pay off the 40,000. He will make quarterly payment into the fund. The account pays 10% compounded quarterly. Find the amount of each payment. Now, very important example. For example, most of the car dealers do not really deal in investment, right? So, in that case, they can give you an offer, or you may have to finance from somewhere else, and this is what it is. Okay. So, now let us see how to figure this out. Now, let's try to understand what is a sinking fund. Now, sinking fund, as talked about in part B, is Peter sets up a sinking fund so that enough money will be present to pay off 40,000. Correct. So you create a fund where you accumulate some money which could be utilized at the end of the term to make a lump sum payment. That's the whole idea. And how did Peter do it? He will make quarterly payments into the fund. The account pays 10% compounded quarterly. Find the amount of each payment. So he can make recurring deposits of smaller amounts over a period of 5 years. And at the end of 5 years, he wants to ensure that there is 40,000 in this particular account to pay off as a lump sum amount. You get the idea. So now you can pause the video and answer this question. So Peter earns 8% simple, Peter has to pay 8% simple interest on 40,000 for 5 years, right? At the end of 5 years, he is going to make a lump sum payment. So this simple interest is 40,000 times 0.08 decimal equivalent, which is 3,200, divided over every year in 2 terms by 2, we get 1,600. So 1,600 is the amount which semi-annually is being paid by Peter. Is that clear to you? Right. So that is the amount being paid. Now let's talk about the part B, which is quarterly payments of R. We need to figure out what should be the payments which Peter can make so that after 5 years he has a sinking fund whose value is 40,000. Now here the future value is known as 40,000. We know the interest which Peter is going to earn is 10%. We're dividing by 4 since it is quarterly, so it gets 0.025. And number of deposits will be 5 times 4, which is 20. Applying to the formula, we know the future value this time, correct? So we'll substitute the future value and the other things known to us and then reverse calculation for the recurring deposit, which comes to 1565.89. So quarterly payments of $1,565.89 will be made by Peter in this particular sinking account. So, sinking fund, as we discussed, is a fund set up to receive periodic payments. These payments earn interest and help pay off the principal on a loan at some time in future, right? So that is the significance. Now let's talk about the energy dues. So this is we are almost at the end of our video, and here is a question which could be slightly difficult to answer at times. So annuities in which the payments are made at the beginning of each time period are the annuities where we call them annuities due, right? Now remember, the compounding period interest is at the end of the period, okay? So it is not an ordinary annuity. Since the payments are made in the beginning of each year, every installment will result into an additional compounding period as compared to the ordinary annuity for the same number of payments, correct? Because you paid in the beginning, so at the end of the year, there'll be interest accumulated on it, right? Now, the question here is find the future value of an annuity due if payments of 1,000 are made at the beginning of each quarter for 6 years in an account paying 8% per annum compounded quarterly. Correct. So I, the value will be 8% divided by 4, which comes to 0.02, and the number of compounding periods are n plus 1 in this particular case. Since they are done in the very beginning, you get the idea, right? So we have 6 times 4 plus 1, so we have 24 compounding periods. Now using this value, so we replace that value of n by n plus 1. But, you know, we got that additional compounding. However, we did not put that additional amount, R, and therefore from the formula we'll take away R. So the formula really gets modified when we talk about annuities due, as you can see here. So the change here is that in the exponent we have n plus 1. However, we have to subtract R one value since we did not really put in that extra recurring deposit, correct? So substituting that into a modified formula, we can find the future value, which comes out to 31030.30. So the future value of the amount due will be 31,030.30 cents. So with that, we come to an end of understanding what annuities are. We discussed about their future value in this particular video. We'll take a present value of annuities and discuss amortization in the next video. So I hope that helps you to understand the concept. Feel free to write your comments, share your views. If you really want to learn from me, you can always send an email to me on the given address, and then we can discuss. Thanks for your time and all the best.